Specifically, we'll look at the boundary value problem f double prime plus f equals h of x on the interval 0 to 1 with boundary conditions f of 0 equals f of 1 equals 0. The first thing we should do is check for homogeneous solutions and make sure that the only solution to the homogeneous problem is the trivial solution f equals 0. So we want to look at f double prime plus f equals 0 on the interval 0 to 1 with f of 0 equals f of 1 equals 0. First, that homogeneous ODE f double prime plus f equals 0 forces f to have the form f of x equals c1 cosine of x plus c2 sine of x for some constants c1 and c2. The boundary conditions, f of 0 has to be 0. That tells us that since f of 0 equals c1, we need c1 to be 0. And then we need 0 to be equal to f of 1. But now f of 1 is just c2 times sine of 1, since c1 is 0. And so that forces c2 equals 0. So indeed, the only solution to the homogeneous version of the BVP is the trivial solution f equals 0. Now we'll construct the solutions to the half BVPs. So we want to solve a problem like g1 double prime plus g1 equals 0 with g1 of 0 equals 0 and g1 of 1 non-zero. And we want to solve g2 double prime plus g2 equals 0 with g2 of 1 equals 0 and g2 of 0 not equal to 0. So in either case, the solution g1 or g2, whatever it is going to have the form, call it now, f of x equals c1 cosine of x plus c2 sine of x, because this is the general solution to both homogeneous problems. So for the first half BVP, what do you need? 0 equals g1 of 0, so that means c1 has to be 0, and you need g1 of 1 to be non-zero, so you need c2 times sine of 1 to be non-zero. Well, as long as you take c2 to be something other than 0, the product c2 times sine of 1 will be non-zero. So just take c2 equal to 1. Don't make your life harder than it has to be. And that'll give you g1 of x equals sine of x. So for the second half BVP, you want g2 of 1 to be 0. So that means you want c1 times cosine of 1 plus c2 times sine of 1 to be equal to 0. And you want g2 of 0 to be non-zero. And of course, g2 of 0 is still that constant c1. So let's try to solve the first equation for c2. Why c2, you might ask? Well, the second boundary condition, or anti-boundary condition, tells us something about c1, so my gut says let's work with c2. So if you want 0 to be equal to c1 times cosine of 1 plus c2 times sine of 1, that tells you that c2 has to be minus c1 times cosine of 1 over sine of 1. And I'm free to pick c1 to be anything I want it to be, as long as c1 is non-zero. So let's clean up c2 a little bit with our freedom on c1. Let's take c1 to be minus sine of 1. Clearly then, c1 is non-zero, and then c2 just collapses to cosine of 1. So we get g2 of x equals minus sine of 1 times cosine of x plus cosine of 1 times sine of x. Now that's a bit of a bulky formula, isn't it? It's certainly more complicated than just g1 of x equals sine of x. But look at the special structure of this formula. It's minus sine of thing 1 times cosine of thing 2 plus cosine of thing 1 times sine of thing 2. And whenever you see a combination of sines and cosines in that way, that should trigger an impulse in you to think about trig identities, trig addition formulas. And if you're in the luxurious position of having time to go to the internet and look one up, because nobody in their right mind ever memorizes trig addition formulas, you will find that this formula for g2 just collapses into sine of x minus 1. And if you had to work with the full sum, say you're on an exam and you can't go look it up, it won't be terrible, but sine of x minus 1 is a lot of a nicer formula for g2 than the mess in the middle. Now we need to calculate the Wronskian of g1 and g2. That's the Wronskian of sine of x and sine of x minus 1. And I claim that that is just equal to sine of 1 once you do the calculations and do a little more trig identities. I will suppress those calculations in this video. So then we use the formula for the Green's function. And here the coefficient on the second derivative in our original boundary value problem is just phi of x equals 1. So the Green's function from its formula from the previous video is this big piecewise mess for g over the interval 0 to 1. And let's fill in the pieces. So when c is less than or equal to x, I have in the numerator g1 of c, g2 of x, so that's sine of c, sine of x minus 1. The denominator, phi of c is always 1, and the Wronskian is just sine of 1. So the denominator is sine of 1. That's whenever c is less than or equal to x. And conversely, for x less than or equal to c, I flip-flop x and c in the numerator, so I have sine of x times sine of c minus 1 over sine of 1. And we are done.